Just this.
So what we looked at today was, what we saw yesterday was how to combine the two neutrino results that we knew into three neutrino results. So we saw that we can define a matrix for U on 3 by 3 matrix. The 3 by 3 matrix took us from mass eigenstates equal to U3 to level eigenstates. Yeah, then we parameterized this 3 by 3 matrix by 3 angles. We assume it was real. So with the matrix here, we said that we can parameterize that by 3 rotation angles. So theta 1, 2, theta 2, 3, and theta 1, 3. So we have this U, which was R 2, 3 of theta 2, 3, R 1, 3, theta 1, 3, R 1. Everybody knows the form of rotation matrix. Okay, 2 by 2 matrices with 1 dimensional views. Then we try to see what we know about these angles through experiments. So the first thing was we looked at reactor experiments like show, which told us that this theta 1, 3 was nearly equal to 0. It actually told us that it's either near 0 or 90 degrees, but we saw that 90 we can rule out. So this is yeah. So very often this theta 1, 3 angle is called as theta reactor. So you might sometimes see this thing called as theta reactor. Then we looked at the atmospheric theta. Okay. So this comes from the evaluation of PE. UV bar goes to UV bar. Yeah. Then we looked at atmospheric experiments. Atmospheric experiments essentially give you the value of P mu. So we saw the expression, looked at an approximate form, and that told us that the theta 2, 3 is very close to theta atmosphere. So in the 2 by 2 case, whatever we call it as theta atmospheric is the 3 by 3 case simply approximately theta 2. And then we looked at R12 of theta 1, 2, so looked at solar neutrinos. In solar case, as we know, it's difficult to calculate PE because there are solar effects. However, so this was of course some sine square theta solar. It's equal. This theta solar angle was we knew before the angle which mixes nu1 and nu2. Then we did a trick of changing the basis from ue, nu tau to ue, ux nu. And we saw that actually ux ui turned out to be equal to cos theta 1 2 sin theta 1 2 minus sin theta 1 2 cosine theta. Sorry. So this told us that the mixing angle between u1 and u2 that we were looking towards, it was this theta 1 2. So therefore this told us that theta 1 2, this implies that theta 1 2 is nearly equal to theta 4. There are corrections because this was true only when theta 1 3 was 0. Okay, so ideally there will be some corrections proportional to theta 1 3. Therefore, very often theta 1 2 is again called as solar angle. So we said that this matrix is parameterized in terms of solar mixing angle, atmospheric mixing angle, and reactor mixing angle. That just we were saying.
Theta 1 3 on the reactor.
0.05 is close to 0. We don't want it 0.
No, I'm not considering it 0.95. I'm not considering
0.95 is good. This is again not possible. So when I say it's nearly equal to 0, it means that theta was sin square theta 13 is smaller than 0.5. So in fact, some of the experiments that are going on right now are trying to figure out what is the value of theta 13. So by no means it is known that it is equal to 0. So all these are very approximate. If you keep in the value of theta 13 as non-zero, this will not be true. And similarly, this will not be true. Okay, so actually, you would say that theta 23 is perhaps approximately equal to theta atmospheric. Theta atmospheric is theta 23 plus something which is order of theta 1 or some system. It is some correction, which I assure you I will ask you to calculate in the next week. Okay, such things need to be calculated. People often say this, but then they forget that it's not an exact equality. In equality, the difference is proportional to theta 1. This 0.05 on sin square theta 13 is inside the current norm. So we haven't gone much better than that.
that is corresponding to the experimental data we are getting from the experiment.
Theoretically, we can think about theta 1. All we know is from the experiment. So actually, the main ingredients in that is, of course, we get this reactor experiment show that I talked about. Then, if you now include this thin neutrino mixing, you can get some bound on theta 13 also from atmospheric experiments. Because ideally, although I said this P mu depends only on theta 23, we saw that it actually has theta 13. Similarly, in the case of this Kamland experiment, which was basically testing non-neutrino oscillations, turns out that the Kamland experiment, the probability of transition, also depends on theta 13 to a small extent. We are going to come to that at some point. So theta 13 is going to affect all these quantities. So theta 13 will be. So theta 13 bounds come from shore. The shore measures EE. It comes from atmospheric neutrinos. Because remember, atmospheric neutrinos, we had P mu. This P mu, I think we saw it was something like 1 minus 4 times u3 square times 1 minus u3 square times sin square delta u2. So here this was 1 minus u mu3 is cosine square 13 sin square, and then it was 1 minus cosine square 13 sin square u3 times sin square. So therefore, cos 13 actually enters in P mu in the case of atmospheric neutrino. So if you don't put it to 0, and if you look at data atmospheric neutrino, you will get some bound on theta 1. Okay, so that is one more input. Another input actually comes from Kamland experiment. Kamland was a reactor experiment, if you remember. It created nu bar to found nu. Okay, so we saw that we had some PEE, and it would be 1 minus sin square 2 theta, which now we know would be 2 theta 1 2, because that is solar, times sin square of theta 2. However, now this is what we will calculate in the next homework. If we actually calculate the value of PE using the complete expression, which actually has 3 terms, right? You have 1, 2, 2, 3, and 3, 1. You will find that there actually are some additional terms. These terms happen to be small, but they depend on theta 1. therefore, when you put a bound on E, you also put a bound on theta 1. So actual bound on theta 13 comes from all these three channels: the show, atmospheric instruments, and comparison. And all three combined give us a bound of whatever we have now. So sin square theta 13 less than 0.15 essentially comes from all these. And because it is small, our parameterization works, because then very clearly one angle becomes atmospheric, one becomes solar, one becomes reactive. Okay, it's a coincidence, and it's not at all sure that it will always happen. It has turned out that nature has been somehow kind to us, and we can parameterize these three angles very simply. Otherwise, they would not be mixed. In the exact situation, they are actually mixed. So what we'll do today is now we'll go to complex mixing method. Yesterday is all real mixing. So first we'll try to see how to parameterize this complex mixing matrix. The mixing matrix by the way is called UPA-, standing for Panteka Go, Maki, Nakadawa, and Saka. And 4 people who here. They came up with this parameterization for the UPA. Then, after looking at that, then we'll see what happens when we go from neutrinos to antineutrinos, because that will give us CP value. So in general, we have all heard this saying that we have complex mixings, then we have got, and then we talk about how CP can be induced by matter. So we come to these things. So let's try to parameterize this matrix. What we know is if the matrix was real, it has 3 mixing angles. That's all we know. So let's see how many parameters actually are there in this matrix. So U is a 3 by 3 matrix. So 9 elements. In general, all elements should be complex. So there should be 18 parameters. Okay, each of these elements actually is 2 parameters. However, U is not any random matrix. It's a matrix unitary. So U dagger equal to 1. So you get U dagger equal to 1 or 3 by 3 U. That corresponds to 9 conditions. So you subtract those 9 conditions from 18 parameters, then you are left with 9 parameters. So this tells us that the matrix UPA- should have 9 parameters. Now we know that out of these 9 parameters, there are only 3 angles. Because if all phases are 0, then it's a real matrix. And we know that angles can tell us everything about real matrix. So if there are only 3 angles, then there should be 6 phases. So this tells us that in addition to the 3 angles, theta 1, 2, theta 2, 3, theta 1, 3, we also should have 3 phases. So therefore, sorry, not 3, but 6 phases. We have 6 phases. So first job now is to try to find out parameterization, okay, which can also have 6 phases in addition to these 3 mixing units. You can't just do any arbitrary parameterization because this one should be able to parameterize all possible 3 by 3 matrices in general. There are in principle infinite ways of doing this. But again, we have to sort of zoom in on a convenient. Okay, just like in the case of angles, we sort of conveniently chose 1, 2, 2, 3 and 1, 3 to get some nice meaning to them. even for phases, we can choose them in a reasonably nice way. So let me give you what a parameter is. So it looks like this. So out of all the things that you see in front, you recognize R12, okay, which is a rotation matrix of 1, 2. You recognize this R23. Notice that this R13 that you had in the middle has now become U13. We'll come to that. But this was the rotation part. In addition to that, on the left hand side and the right hand side, you have got what are called as phase matrices. A phase matrix is meant the following. So when I say phi of chi1, chi2, chi3, it basically means I have a diagonal matrix. It e to the power I chi1, e to the power I chi2, e to the power I chi3. Similarly, when I say phi of, so this should be phi of phi1, phi2 and 0, I mean this is e to the power I phi1, e to the power I phi2, and e to the power 0. That's one. So that's the convention. So let's notice a few things. Okay. One is that both of these are diagonal matrices. Second thing, so let's say this central part is a triviality matrix. Okay, so let me write it down. So I have a central matrix, which is a triviality matrix. Now when I multiply this matrix by e to the power I chi1, e to the power I chi2, e to the power I chi3, let me just write this thing like this. What will this do? So let me multiply this. So this is e power I chi1a, e power I chi1 times e, e power I chi1 times c, e power I chi2 times e, e power I chi2 times e. So what this matrix does is this phase multiplies the first row. This phase multiplies the second row. This multiplies the third row. So these three are often called as row phases. Okay, because they multiply the row. So these somehow sometimes are called as row phases. Because they multiply rows. Similarly, if I have and if I have on the right hand side e power I phi1, e power I phi2, 1, then I have a e power I phi1, b e power I phi2, c, so b e power I phi1, e power I phi2, f, that's all. So these phases are column phases, so they multiply columns. These are informal names for it. I'll tell you what the formal names are. You can call it in the row and column. So these are the two matrices that deal with rows and columns. Okay. Now let's look at the central matrix that looks very similar to our earlier real matrix, except that there is one extra phase data inside. What is this data? So R23 and R13, sorry, and R12 are exactly what we had earlier. However, here instead of R13 we have got what's called a U13, which is defined like this. So remember, if I put data equal to 0, this reduces down to R13. Okay. So what I have done is put e power minus I delta here and e power I delta here. This is also a rotation matrix, it's a complex rotation matrix. So this happens to be one of the ways that parameterizes this V matrix completely. It has three rotation angles, theta 23, theta 13 and theta 12. It has 6 phases, 1, 2, 3, 4, 5 and 6. And right now, just take it from me that this indeed is a more general matrix. Now let's go to what this phases do. So firstly, we have complete freedom in choosing what are the individual phases of u1, u2 and u3. This you must say. Okay, so this is what I have. Okay. So let's go step by step. So UPM is I divide it into 3 parts. I put on these row phases here, the column phases here, and this part which consists of rotations in 1, 2, 2, 3 and 1, 3. I write them as UJJ. So now, no one has told us what is the phase of u1, u2 or u3. It's our own choice. So even if I multiply, so when I multiply, so let's say I have u1, u2 and u3 at some complex group. If I multiply all of them by a complex number, the same complex, same phase, nothing is going to change physically. It just says that my definition of the common phase, definition of u1, instead of saying it was u1, it was u1 times e to the power n. So such a transformation where I multiply u1, u2, u3 by a common phase, constant common phase, is very trivial. Okay, that will do nothing to UPM. Okay, sorry, to UPM anything, do nothing to physics. Okay. So therefore, I don't need, so in principle general I could have at e power I51, e to the power I52 and e to the power I53. But because I can do this, I can always absorb that into this. Therefore I don't need 5. That's one way to look at why I seem to have 3 phases on this side and only 2 on this side. But anyway, so there's no need of 5. What we see sometimes people doing is they don't keep 5.1 and 5.2, but they keep 5.2 and 5 in their choice. Okay, so sometimes you will see people parameterizing things. You will see everything. You will see 5.1, 5.2, 5.3, or you will see 5.1, 5.2 and 0 here, or you will see a 0 phase here and 5.1, 5.2, 5.2, 5.3. So you will see many such phases. As long as you are consistent with one, you see. Now let's look at these phases, okay, the row phases. Now what do row phases do? Suppose I guarantee you that I can change the phases of u mu and u tau independently of each other. Okay, so I can change the phase of, define the phase of mu whichever way I want, mu whichever way I want, and u tau whichever way I want. Okay. What does that mean? That means that then I can absorb chi1, chi2 and chi3 into u1, u2 into mu and u tau. So people agree or I can always decide that instead of calling electron nucleus as mu e, I call it as mu e times e to the power minus I chi1. Okay. And then when I multiply this by e power I chi1, mu e stays mu e, but this I chi1 disappears. So if this is a big if, okay, that's why this if is in red. If I guarantee you that I can change phases of mu e, mu and mu tau independently, that's very important. Independently is very important. See, earlier when we argued about this phase, we had to change the phase of mu1, mu2 and mu3 simultaneously. Okay, so that's the independent matrix. We are not talking about that. We are now talking about changing mu e whichever way we want, mu whichever way we want, and mu tau whichever way we want. Okay. If you are able to do that, then you can rotate away chi1, chi2 and chi3 and they can become 0. So you don't have to worry about it. Now, whether we are able to do this or not, actually depends on your theory of flavor. So it depends on on what is your Lagrangian of your model. The standard model you can always use. If you have no new physics, only a standard model, this is always possible. However, since we have neutrino masses, very often we get theories of neutrino masses which involve physics beyond standard model, and then it's not guaranteed that it is possible. However, for our practical purposes, one can take these chi1, chi2, chi3 to phases which can be rotated around in a not of much consequence. Therefore, these what I call as flavor phases are often called as unphysical phases. So if you only look at neutrino oscillations, they will not matter. In fact, if you only look at any neutrino experiment at low energy, they will not matter. So in principle, they are irrelevant. Therefore, they are often called unphysical phases. Okay? And then people no longer think about it. So we can between that for some time till maybe after 1 month or so, we can rethink whether they actually can have some consequences. But for all practical purposes, at this point of time, we can consider them as irrelevant. Consider that we can be rotated independently. Okay. So these are so-called flavor phases, chi1, chi2. Now these column phases are the so-called Majorana phases. Okay. Again, this was a German guy, therefore Majorana, not Majorana. So, is there some way we can get rid of these phases? And the claim is the following. Again, if I guarantee you that I can change the phases of mu1, mu2 and mu3 independently, so mu1 by sum of 1, mu2 by sum of mu3 by sum, if I am allowed to do that, then yes, then I can absorb them into mu1, mu2, mu3 and therefore put phi1 and phi2 to 0. So my expression becomes simple. But this condition is very important because, again, in many models of new physics, which give you Majorana masses, for example, these rotations are not possible. So, again, when we look at Majorana neutrinos, maybe after 1 more month, we will see examples where it is not possible to rotate phases of mu1, mu2, and mu3 independently. So, we will see why that happens. But right now, let's just say that if they can be rotated independently, then phi1 and phi2 can be made equal to 0. Now what is left now? So these 5 phases can therefore be made 0, at least under certain conditions. What is left is the Dirac phase delta. So in the UPMNS, we had this phase delta. Turns out that there is absolutely no way that you can rotate this phase again. It always exists. So it's a very, very physical phase. It's a phase which will be observable in any oscillation experiment. And as we will see in the next 10-15 minutes, that this is the phase which will generalize to CT parameters. So this is always observable in oscillation experiment. So now we have the parameterization. Okay, so we will put in all these phases and angles and so on. So with this parameterization, now we will see what happens to the probability of mu alpha going to mu beta. This is the master equation that we had seen just right? So there is delta alpha beta, this no oscillation part. The second part is 4 real part of this bracket, and then we had this sine square delta gi. And your second term which had imaginary parts of this. So whatever we did yesterday, we only talked about this part. Okay? We didn't care about imaginary part because all U elements were real, so there was no imaginary part. Yesterday thing was simple. Today you have to be slightly careful. Firstly, look at this bracket alpha beta ij. Okay? This is the definition. Now I want you to notice one thing about this definition. Look at alpha. One of the alpha elements has complex conjugation, other one does not. One of the beta elements is complex conjugated, other one is not. Similarly, one I is complex conjugated, one is not. So what does this mean? This means that, let's talk about alpha. Let's say alpha stands for
other one is not. Does it done with three?
J, see, I appears twice. Okay. Whenever I appears once, so one of those, so there are two elements which involve I. Okay. One of those is complex conjugated, other is not. Similarly for alpha, beta, I and O. So it's true for all four of them. So what does this mean physically? Let's say I have a flavor eigenstate mu alpha. Okay. Now, so I told you that sometimes I can rotate the phase of mu alpha, whatever, wherever I am. So mu alpha, let's say I change it to e to the power I some good thing here. This one some good Greek alpha. Okay. Many of them are. I think beta
Lambda.
Lambda. E power I lambda times mu alpha. Let's say we do this. So what does this mean? If I transform like something like this, okay, then it means that my UPMNS has to change by some phase. So this means that my U alpha I becomes e to the power minus plus I lambda times U alpha. Because U alpha I, so U alpha is U alpha I times U alpha. Okay? So if my U alpha goes to e power I lambda times U alpha, then to get this factor, my U alpha I should also change by this factor, e power I lambda. Okay. So this seems to change my U matrix. No. Okay. But now, look at what happens to U star beta j. Sorry. U star alpha j, since it is a complex conjugate, now will become e power minus I lambda times U star. So what does this mean? If I take a product of U alpha I and U star alpha j, this will not change. This happens for alpha. But the same argument applies for beta. So therefore, I can change beta phase and the bracket doesn't change. Similarly for nu I, it doesn't change. See, now I'm not using the condition that I can change independently or not. So the condition doesn't apply anymore. Even if I can change the phases independently or not, this is always valid. So bracket is therefore what is called as a rephase invariant. This bracket is called as a rephase invariant. What this means is that if you are allowed to change the phase of mu alpha, mu beta, whatever, do whatever you want, the value of bracket will not change. So therefore, this expression, now it should be clear as to, see, P alpha beta is an observable quantity. Observable quantity should not depend on what conventions you use. So it was very important that whatever we write here should be independent of any conventions. And because the brackets happen to be independent of any phase conventions, they are the right quantities to have. So it's not a coincidence that you only add brackets. So it was extremely relevant that you only have brackets. That's because these brackets are not affected by chi1, chi2, chi3, phi1 or phi2. So you could even try to do it for yourself. Find out the values of this and you will find that chi1, chi2, chi3, phi1, phi2 just disappear. They are not a part of this. Only the Dirac phase delta is there. To find out what is bracket is delta is here. So this of course is what we have done for propagation in vacuum. But even when we propagate in matter, the same thing applies. Even when we propagate in matter, you will see that this bracket will always be independent of phases, and moreover, it will be independent of chi1, chi2, chi3, phi1. So what does this mean? This means that although I had all these 6 phases, when I do oscillation experiments, this is very particular to oscillation experiments. Okay, so this is alpha going to as long as you are doing an oscillation experiment, you will not have to worry about chi1, chi2, chi3, phi1 and phi2. Whether they are physical or not, or relevant or not, is completely independent. These phases will not appear in your parameter because they will not appear in your brackets. So therefore, when we do oscillation experiments, we never consider chi phases and phi phases. We only consider this u tilde. So this u tilde was R23 of theta 23, U13 of theta 13 and delta, and R12. So very often people don't even mention this. People don't even separate this u tilde PMNS. People often say that u tilde PMNS is just equal to this. So in many papers and many books, you will find the definition of UPMNS to be simply equal to this. They will not mention the phi phases and the chi phases. That is because if you are talking of only of oscillation experiments, it doesn't make a difference. So now, till now we looked at UPMNS. This UPMNS took us from U1, U2, U3 to Nu-E, Nu-B, Nu-T. So it took us from neutrino mass eigenstates to neutrino level eigenstates. Now let's see what happens to antineutrinos. Okay, because finally you will experiment with neutrinos and antineutrinos. So you will take care of what happens. So let's see what we do when we go to antineutrinos. So we are trying to look at probability of nu I going to nu alpha. U I alpha. U alpha I. It's something like this. So nu I is coming in and figure out what is the fraction of u alpha. Let's plan u alpha. Now you know of CPT theorem. CPT theorem says that if your process A to B, look at the process B bar going to A bar, then they should have the same amplitude. Okay. Roughly speaking, it works here, so I won't try to give you the actual statement, but this suffices for me. So if A goes to B has a certain amplitude, then D bar going to A bar, we have the same as CPT theory. And as far as our the local field theories are concerned, it's valid. This means that mu I to mu alpha is the same as mu alpha bar to mu I bar. So I change particle to antiparticle and I change the time reversal. Okay, so particle to antiparticle is Cp and time reversal is T. So CPT tells me that this is true. Okay, this is mu alpha bar to mu alpha. And now simple quantum mechanics tells you that if I change the bra and fit, I get a complex conjugate. AB complex conjugate is BAB. So therefore, this is equal to this quantity. But again, what is this quantity? This is u bar alpha I. Right? Because what has happened now? Instead of mu I and mu alpha, we have got mu I bar and mu alpha bar. Okay? So what I have got now? That u alpha I is just u bar alpha I complex conjugate. This is the same. Agree? So therefore, whenever you want to go from neutrinos to antineutrinos, all we need to do is make complex conjugation. So that's u alpha I is equal to u bar alpha I star. So now it should be clearly obvious how we will write UPMNS for antineutrinos. Just complex conjugate all the units. What does that mean? Whenever you have a phase e power I chi1, make it e to the power minus I chi1. That's complex conjugation. So chi1 goes to minus chi1, chi2 goes to minus chi2, chi3 goes to minus chi3. So all flavor phases will change sign. Similarly, this phi1, phi2 will change sign. You see, all phases will change sign. So phi1 goes to minus phi1, phi2 goes to minus phi2. Dirac phase will change sign, it's also a phase. So delta goes to minus delta. Thetas are missing angles. They are not complex, they are real. They don't change sign. So they stay the same. And the bracket, which was alpha, beta, ij, now becomes its complex conjugate. Because each element has become complex conjugate. Okay, so product of complex conjugate of element is complex conjugate. So bracket goes to bracket star. So that's what you do when you go from neutrino to antineutrino. So now we will see what happens if we try to write down the Jarlskog probability of neutrinos and antineutrinos. So this one is u alpha going to u beta. This is the expression that we always had. This was delta alpha beta, real part of bracket sine squared minus 2 times imaginary part of bracket times sine of delta. This we always had written. Now we want to find out what happens when u alpha bar goes to u beta bar. We know what happens. This delta alpha beta will of course stay delta alpha beta because it doesn't change. Bracket goes to bracket complex conjugate, which means that real part of bracket stays the same, imaginary part of bracket changes sign. Okay. So therefore this factor stays the same. The third factor changes sign. So only difference between neutrino probabilities and antineutrino probabilities is that this third term changes. This is the reason why this third term was called as equality, because it separates between u alpha to nu beta and u alpha bar to nu beta. So if I write down the difference between them in terms of probability, p alpha beta minus p bar alpha beta, okay, that is equal to this mode factor, imaginary part of bracket times sine of 2 delta G. So the only difference between neutrino transition and antineutrino transition happens due to the imaginary part of the bracket. So therefore this is the relevant quantity when you talk about CP validation. So everyone agrees that this quantity is a valid quantity. We just neutrino quantity. So this is the relevant quantity, imaginary part of the bracket. This imaginary part of the bracket happens to have a very nice property, and an extremely useful property for our work. This is that it's a constant.
We can measure this
to some extent, yes. Because you cannot really measure P alpha beta directly. What you measure is number of events. So this P alpha beta comes multiplied by, we used to write this thing sometimes, right? So what you measure is n alpha. Yes, okay, actually maybe I can find it. It's very old one. Maybe it won't be. So take this as P alpha beta. Okay. Now this comes multiplied by the flux, the cross section, and this resolution function. Also some efficiency, something I forgot. Okay, so maybe it should also have the efficiency factor. Check for that efficiency of maybe so if all the other factors are the same for nu and nu bar, can you actually measure P alpha beta minus P bar alpha beta? Normally they are not the same. Normally other factors are different. So you cannot directly measure this quantity, but still this quantity is a measure of, you should aim towards measuring this quantity. In principle, this is the quantity that you want to use. Practically, it is difficult, but theoretically, it is. Now to the interesting reason. See, when I say, okay, let me tell you why it's called bracket. It's called bracket because of the things. Here is 3x3 matrix. So these are u alpha, these are nu top. This is now let's say you want bracket alpha beta ij is equal to u alpha I u beta j. That's so good to remember how to write this. Okay, so you write down just pairs. Then you invert the pairs, say u alpha j, u beta I, and you complex conjugate. So let's take for an example. Okay, let's take alpha equal to e, beta equal to mu. Okay. And I is equal to 1, j equal to 2. So then this u alpha I is this number. U alpha I. Then I have got u beta j, which is mu2. So it's something like this. Then I have got u alpha j star, which is here, and u beta I star. Square means it's complex conjugate. So you see that basically you are taking 4 elements inside a square, okay, and calculating them. Okay, so the square is like a black, so that's why it's called black. If you had chosen something else, you would not have chosen these 4 elements, but maybe you would have chosen these 4 elements. You would have a rectangle like this. Okay, or you could have chosen these elements. Or you could have chosen maybe elements in the column. So, bracket means choose any rectangle inside a UPMNS. Okay. Make 2 of those corners as complex conjugates and find out. That's what bracket means. Now, if you go back to our UPMNS, so let me show you what UPMNS is. Here, for example. So look at this UPMNS. In general, bracket should consist of these 4 elements. So this could be the rectangle in one, or this rectangle, or this big rectangle, or this rectangle, whatever. In principle, you would say that depending on which rectangle I choose, I will get a different number for the bracket. It's indeed true that the value of bracket will depend on which rectangle you choose. However, what is important is that if you calculate imaginary part of this bracket, it doesn't depend on which rectangle you choose. This is a very special result. It is true only because we have 3 generations. It would be not true if you had 4 generations. But you can show that for 3 generations, this quantity does not depend on which rectangle you choose. Up to a sign, so it is plus minus. So you can go to that parameterization or UPMNS, pick up any rectangle and calculate the bracket corresponding to that rectangle. What you will find is that that quantity will always be equal to this. Sine 1 2 times cosine 1 2 times sine 1 3 times cosine 1 3 times, sine 2 3 times cosine 2 3 times sine 1 3 times cosine squared 1 3 times sine of it. So to go and do your experiments with UPNS matrix, you will find that whatever you do, whichever bracket you choose, the imaginary part is always constant. Okay, this can come with a plus or minus sign. That is of course much. So this J is called as Jarlskog invariant. Again, this is a Swedish lady, so therefore Jarlskog and not Jarlskog. So J is the Jarlskog invariant. This J is independent of alpha, beta, I and J. We already saw that the bracket was independent of phase changes. That's a different matter. Imaginary part of bracket is independent of which row and which column you choose. So this is what this is. And then you see that CP violation, which was something like this quantity, is therefore always proportional to the value of J. And it will be just multiplied by sine of delta Ji with some plus minus signs. The plus minus signs will depend on what is your experiment. Okay, but this J will always stay constant. So whenever you say you are going to calculate CP violation, you are trying to look to calculate this quantity. So now you will see that, well, firstly, we know what is sine 1 2, right? It's sine of theta 1 2 near the 0.3. Okay. We know what is cosine 1 2, 0.6. Well, no, okay. Sine 1 2 is 0.6, cosine 1 2 is 0.8. Sine 1 2 3 is like 0.7, 1 by root. This is 1 by root. So they are the order of 1. we don't know what is sine 13. And very clearly, if sine 13 is 0, it is not a CP violation. So lesson we get is that if theta 13 is 0, we cannot have CP violation. Therefore, so before we go ahead and try to build an experiment which tries to measure CP violation, first you should check if theta 13 is 0. Therefore, measurement of theta 13 is very important. You want to decide whether you want to have an experiment which measures the value of CP violation. So that is very important. Second thing, which again should be obvious, is if delta is 0, this is 0. This is clear because if delta is 0, then you have no complex phase. So everything is real. So CP violating quantity is always proportional to sine delta. So any quantity that you see CP violating quantity is always proportional to has a theta 13 dependence and it has a sine delta dependence, not any delta by the way. So note that CP violation means sine delta, not any delta. So we will always have theta 13 times sine delta. So later on, when we try to calculate the expressions for CP violating quantities, you will see that everything that we get, which is CP violating, will have a theta 13 and it will have a sine delta. So if they are 0, you will not get this. So now to certain extent is very straightforward. We know the master equation. No? We know this P alpha beta is some blah blah blah. Some delta alpha beta minus some bracket. You just put in the values of your U alpha beta, or U alpha R, U alpha J, blah blah blah. You will find what is the probability of yourself. If you can do it fine, then you will do also. This is fine. So now we'll start thinking about actual experiments which will be able to detect this CP violation. There are already some experiments which can detect theta 12, which is solar and from that. We saw experiments which can detect theta 23, which was atmospheric experiments, and then this Dinos at K2K. There is an experiment which can measure theta 13, which was this reactor experiment like show. So now we have to go forward and look for an experiment which can measure the value of delta. That's going to be our next step. We also need experiments which can measure the value of theta 13 more accurately. And we also want to measure experiment which can tell us what is the mass ordering, normal and inverted. Okay, sine of delta n square. We don't know. So usually such experiments will consist of having certain source and the detector. Now to have better accuracy, again you will see that sometime next time, you usually need longer baselines because whatever can be done with short baselines has been done. Okay. Experiments at distance of 1 kilometer have been done, which was like this show. Experiments at the distance of 200 kilometers have been done, which is atmospheric experiment, this K2K. Experiments at the level of 1000 kilometers have been done. This was this Minos experiment. So these have been done. The time has now come to build experiments which have a baseline of much more than 1000 kilometers. 2000, 3000, 5000, 10,000 and so on. And when you go to such high distances, the one major element it enters is that now these beams can no longer pass through air. They have to pass through the earth. It's also true for if you are distance of 200 kilometers. But for 200 kilometers, you always pass through the earth. However, the longer you go through the earth, the longer you are affected by matter. So therefore, it's very important that now when we do talk about such long experiments, we have to talk about what happens inside the earth. even in INO, okay, so although we don't have the neutrinos that come from below come through Earth, right? So they travel through matter. When we did atmospheric neutrinos, we only considered nu-neutron mixing, so we were safe. Because for nu-neutron mixing, the Earth says nothing, just passes. Okay, the potential is zero. Now we have to do everything by using thin neutrinos. This means that we can no longer neglect Earth effects. So even for atmospheric neutrinos, we will have to take into account what happens to neutrinos when they pass through. So therefore, we will see what happens when matter comes to it. The reason I brought matter in right now is because matter can induce CP transition. Okay. See, matter is inherently CP asymmetric. Because no matter has protons but not antiprotons. It has electrons but not positrons. So matter is CP asymmetric. So let's see how that affects neutrinos. So we know that for neutrinos, there is the charge current potential, which is Vc is root 2 Gf times He. And this happened because we had a charge current interaction that went like this. So we had E coming in, electron going out, charge current. So you have to calculate this process. Now, if they are antineutrinos, this process doesn't happen. Of course, we do not know that comes. What happens, however, is something like this. You have a UV coming in and an electron coming in, W. Going out, UV parts also. And this is outwards like this. So the two reactions are different. The amplitudes are different. The amplitudes differ by factor of -1. So you have to calculate this. Only vertices won't give the answer. So therefore, the value of matter potential for charge current will be different for UV and for UV. So again, I will give you simply the answer and not show you why. This has to do with interchanging of fermions with a minus sign. So for neutrinos, we do this. That Vc is root 2 times Gf times He. For antineutrinos, you get a minus sign. So matter potential for antineutrinos is exactly opposite of neutrinos. Minus 2. So there is some difference. Similarly, if you put neutral current, then the potential for neutrinos was minus GFNN by root 2. But if you go to antineutrinos, that gets negative sign. So it's negative sign disappears. So there is again some relative negative sign. Ne was number density of electrons, and N is number density of neutrons. So remember, neutral current potential depends only on number density of neutrons. common electrons. So electron and protons actually cancel out. Yeah, this was in some lectures. Right. So in matter, therefore, potentials exactly change sign. So Vc goes to minus Vc and Pn goes to minus Pn. And nu goes to nu bar. Now these are some interesting consequences. So let's write down the value of mixing angle in matter. So what I have done, this is mixing angle between electron, neutrino and something else. So nu e, let's say nu e dB is. So all that happens is this Vc, here is Gf Ne by root 2, so Vc by 2. And here it is Gf plus Gf Ne. But now let's stare at these equations and we'll find certain. If this is positive, if these two are of the same sign, then theta will increase. It is the two term, right? The delta considered as one term, this is the second term. If they have the same sign, then inside matter theta will increase. Okay? Because tan theta will increase. But if tan theta increases, here, since now they have the same sign, tan theta m bar will decrease. So therefore, if inside matter mixing angle for neutrinos goes up, then mixing angle for antineutrinos goes down. Okay, it is no longer symmetric. That is exactly what I say. Which means that, okay, we saw that when this is equal to this, we get a resonance. It's MSW resonance. If resonance occurs here in the neutrino channel, it means that these two are equal and have the same sign. That implies that resonance cannot happen here. Okay. In fact, it will mean that mixing is actually suppressed. Because both of these are the same sign. So therefore, whenever resonance occurs in matter for neutrinos, the antineutrino mixing becomes suppressed. Resonance means angle 90 degrees. Nu becomes 90 degrees, then nu bar mixing angle becomes very small. Similarly, the other way around. If there is a resonance in antineutrinos, your neutrino mixing will be very, very small. So matter gives you this distinction between neutrino and antineutrino. Another thing is the following. See, I have this delta here, but I haven't told you what is the sign of delta. If I change sign of delta to minus delta, then tan theta will become this, and theta m bar becomes this, and theta m becomes this. So, in one sense, if you want to go from nu to nu bar, it is almost like changing delta to minus delta. So going from nu to nu bar is like going from delta m square to minus delta m square. This sort of means that now you don't know sign of delta m square atmosphere. If it was positive, you see how neutrinos behave. Antineutrinos will behave exactly the same way if delta m square atmosphere was negative. Okay, so there is this correspondence between nu for positive delta, nu bar for negative delta. Therefore, if delta is greater than 0, then this is greater than 0. So if delta is greater than 0, you get enhancement of mixing angle for neutrinos and depletion for antineutrinos. If delta is less than 0, the mixing angle is enhanced for antineutrinos and depleted for neutrinos. The effects can actually distinguish whether delta is positive or negative. So what do? To do an experiment where you determine what happens to neutrinos, what happens to antineutrinos. Look at which seem to give you larger mixing angle. If neutrinos give you larger mixing angle, then delta is positive. If antineutrinos give you larger mixing angle, delta is negative. Again, this is exactly what INO is planning to do. INO is based on this straightforward principle. That if delta is positive, neutrino mixing will be larger. If delta is negative, antineutrino mixing will be larger. So this is the basic principle of INO, and then you put in everything else. Then you put in the atmospheric neutrino flux, blah blah blah, probability of survival, and so on. But the basic principle is this. This is the reason to distinguish between delta less than or greater than 0. You need a detector which can distinguish between nu and nu bar. See, till now what happens at super conducting, however big the detector is, you cannot distinguish nu and nu bar. Since you cannot do that, you just add them up. So you cannot do this simple experiment where you just measure nu and nu bar separately and figure out what is the effective mixing. So I know we do exactly that.